Once again, you're welcome to Waidsum Academy. Today, we'll be looking at part 2 of our nuclear physics, radioactive decay. So today we'll be looking at the nuclear physics, and we're looking at the part 2, which is radioactive decay. So before we move on, let's listen to this tutorial before we move on.
Let's get into this video on decay equations. You may recall nuclide notation. Alpha, beta, and gamma radiation can be represented in this form. Let's begin with alpha. Alpha particles consist of 4 nucleons, that's 2 protons and 2 neutrons, so the mass number is 4. Those 2 protons mean its charge is 2, and its atomic number is also 2. Beta particles are just electrons, so they have no nucleons, and their mass number is 0. They have a charge of -1, so their atomic number is -1. Gamma radiation is a form of electromagnetic radiation, so it has a mass number of 0 and an atomic number of 0. You need to learn these 3 from memory to be able to answer these questions in an exam. It is useful to be able to write decays as equations. Much like a chemical equation, the left side features our initial particles, the parent nucleus here. An arrow represents the decay occurring, then we write our products. These are the daughter nucleus and the form of radiation that has been emitted. It's an alpha particle in this case. An important rule of decay equations is that the number of nucleons is conserved in a decay, so the total mass numbers before and after must be equal. The initial mass number was A, so to make the final mass number A, the daughter nucleus will have a mass number of A minus 4. Similarly, charge must be conserved. This means the atomic numbers either side of the arrow must be equal. This makes Y's atomic number Z minus 2. These rules also apply to beta decay and gamma decay. Gamma has no mass or atomic number, so the element is unchanged. The nucleus just becomes less energetic. Questions on this topic in an exam will often ask you to write out the decay equation given a few pieces of information. Americium undergoes alpha decay to form neptunium, which has the chemical symbol Np. Write the decay equation for this process for 3 marks. First, let's note that this is alpha decay. The first step is to recall the alpha particle's mass and atomic numbers. These are 4 and 2. Next, write the information we already have into the decay equation. We know americium's chemical symbol, and we know neptunium and an alpha particle are the products. Remember that mass number is conserved, so americium's mass number is the sum of neptunium's mass number and the alpha particle's mass number. Some quick rearranging shows us neptunium's mass number is 237. This is 1 mark. Total atomic number is also conserved, so we do the same thing. This shows that neptunium has 93 protons, which is our 2nd mark. Finally, we stick these 2 values into our decay equation. And there is the final answer. This, all written out correctly, is the 3rd mark. Don't take any chances with the easy calculations and write it out. You'd be amazed how many students will add 241 and 4 instead of subtracting. Let's have a look at a different type of decay now. Tritium is an isotope of hydrogen. It decays to an isotope of helium via beta decay. Write the decay equation for this process. So, this is beta decay. Let's recall the atomic and mass numbers of a beta particle, which are -1 and 0 respectively. Again, we'll write out the decay equation, leaving gaps for the helium isotope's atomic and mass numbers. As with the first example, we'll equate the mass numbers. showing that the helium isotope has a mass of 3. And that's mark 1. The same tactic for atomic number shows that the atomic number of helium is 2. You should always take extra care with the beta particle's minus sign. That's our second mark. Finally, we put all of that into the decay equation, which leaves our answer. And that's our third mark. In this video, we covered the different mass and atomic numbers associated with alpha, beta, and gamma radiation. We explained that charge and nucleon number are conserved in a decay, and that, as a consequence of this, total mass and atomic numbers before and after the decay must be equal. Don't forget to check out all our other fantastic revision resources at Save.
Okay, so that's the tutorial on the decay equations for alpha, beta, and gamma. Okay, first of all, before we go on the decay equation itself, let's have an overview. Okay, the overview on the effect of nuclear size on the decay. The effect of the nuclear size on the decay. We normally say most of the stable nuclei, they have same number of protons and the number of neutrons. So when you're stable, it means your number of protons and nucleons are probably same. But the moment there's a difference between your number of protons and number of neutrons, then you start to feel unstable. You start to feel the instability. So that instability, you want to break. You want to disintegrate. Okay? So that instability creates that repulsive force. That repulsive force that you want to pull away. They want to pull away from each other. Once the number of protons and number of neutrons in an atom, they are not same, then the atoms start to feel unstable, The atom want to disintegrate, want to break. That there will be a repulsive force that is created by the difference that you are having between the positive charge and the zero charge. So you start to feel this difference, okay? And this will cause the nucleus to repair when it becomes very large. When the number is growing big, with the difference between the protons and the neutrons are getting larger and larger, the difference is getting big, then it will create a larger repulsive force that will break the atom into smaller units, a daughter nuclei, what we call the daughter nuclei. So the first unstable nuclei is called the parent nuclei. So with more and more instability happening to the nucleus, the protons and the neutrons are growing farther apart from each other. The more this happens, the more the nuclei begins to feel very unstable, and the more they have a repulsive force that wants to break them into smaller units. And when this happens, we say an isotope is formed. Okay, we can therefore say that the nucleus has an imbalance of proton we can say that it has an imbalance of proton. Just a minute. We can therefore say that the nucleus have an imbalance of proton, okay, and neutron, protons or neutrons. So they are not. The more they grow farther, the proton and neutron, the more it becomes unstable. And the more is more likely for the atom to decay, to break into smaller unstable, into smaller units, until it gets to stability. Until it gets to stability level. Okay? But as long as the protons and the neutrons still get farther apart from each other, then this nucleus remain unstable. The nucleus remain unstable. Okay? Now, so isotope, in other words, is an element with the same number of protons but different number of neutrons. That's obviously what we call an isotope. Element that have the same number of protons but different number of neutrons is what we call isotope. So, for an element to even be unstable, it must become isotopic in nature. For a nuclei to become unstable, it must become isotopic in nature. Why? Because we said when the number of protons and number of neutrons are not same, then the atom begins to feel instability, begins to become unstable. Okay? Unstable to the extent that there will be a repulsive forces between the proton and the neutron. Try to pull apart, try to break, okay? And what eventually break out is called a decay, an alpha decay, or a beta decay, or a gamma decay. Okay, so whatever breaks out is what we call the radioactive decay. Okay, whatever breaks out from it. So we say isotopes of element may be radioactive due to one of these reasons, one or two of these reasons. It may be radioactive due to elements is said to be radioactive when the atomic number becomes too high and it starts to feel a big difference between the number of protons and the number of neutrons. So we say one of the reasons is due to the excess of proton or neutrons in the nucleus. When an atom has too many protons or too many neutrons in its nucleus, it will start to feel unstable. That's one reason. Another reason that isotope become radioactive. Another reason why an isotope becomes radioactive is when the nucleus is too large. The nucleus itself is too large. When the nucleus itself is too large, then the isotope will become a radioactive isotope. So it's either the nucleus is too large, or we say there is excess of proton or neutrons in the nucleus. When there's excess proton, additional proton, or additional neutron, even if it's not too large, when you have extra proton or extra neutron in the nucleus, then we say the isotope is radioactive. Okay, we say the isotope. Now let's take a look at hydrogen. Hydrogen isotope. Let's take a look at hydrogen isotope. Hydrogen, we have hydrogen 1, which is the stable one, the stable hydrogen, the stable nucleus. Okay, the number of proton is 1, the electron is 1, the mass is 1, but the neutron is 0, because neutron is always the mass minus the proton. Number of neutrons is always the mass number minus the proton. For example, well, let's say we have hydrogen in this. Okay, let's say this is hydrogen, right? The hydrogen atom itself with isotope 1. Okay, so if we have this, the top one is the mass number or the nucleon number. So this is the mass number. While the bottom one is the atomic number. This is the mass number. So number, we just use NO. This is the mass number, the top one. This bottom one is the atomic number or the number of protons. Remember, atomic number is same as the number of protons. So to find the neutron, the number of neutron is always the mass minus the atomic number or minus the number of protons. Okay, it's always the mass minus. So if I want to find small n, the number of neutron, I will say the mass is represented by letter A. Okay, and the number of proton or atomic number is represented by the letter Z. So when you say the mass minus the atomic number, you get the number of neutron. So to get that number of neutron, you simply say the mass is 1 minus the number of the atomic number is 1 also. So we get 0 for neutron. So there's no neutron in this regard. There's no neutron. Okay, so since there's no neutron, we say this is one of the state of hydrogen. Okay, hydrogen 1. Now let's take a look at the second hydrogen when you have the one you call the deuterium. Deuterium, the second isotope of hydrogen, has 1 here and 2 here. Let's change, I think, for clarity. It has 2 here. Okay, like if we want to find the number of neutron, we always say the mass number or the nucleon number. This is called mass number or nucleon number, which is represented by letter A. The mass number minus the atomic number. The mass number minus the atomic number. So which is N is equal to, the mass number is what? 2 in this regard. The mass number is 2. So 2, in this case, it will be 2 minus 1. And then the neutron number will eventually become what? 1. 2 minus 1 is 1. So for this case, the second isotope of hydrogen, you have the neutron is 1. So here neutron is 1, proton is 1, electron is 1. For this case, proton is 1, electron is 1. Proton and electrons are same, are equal. That's why an atom is said to be electrically neutral. Number of protons is equal to number of electrons. So if proton is 1, the electron is 1. So to find neutron is the mass minus the mass number minus the atomic number or the number of protons. So you get the neutron. What of deuterium? No, this is deuterium, the tritium, the third isotope of hydrogen. We changed the stethoscope. The third isotope of hydrogen for deuterium, tritium. This is the isotopic nature. Okay, to find the number of proton, we know proton is 1. For this one, proton is 1. Proton equal to 1, or proton equal to electron, and both of them equal to 1. Why we say that? Because proton is 1, electron is 1. Okay. Similarly for this one, proton is proton equal to electron, number of proton equal to number of electron, and both of them also equal to 1 in this regard. Same for the first one, right? Because here is 1. So number of proton equal to number of electrons, number of proton equal to number of electrons, and both of them equal to 1. Even though here, in this first case, the neutron is 0. Number of neutron is 0. And in the second case, number of neutron is 1. So in this second case, proton is 1, electron is 1, and neutron is 1. All three of them are 1, 1, 1. Then the third case, for the third isotope of hydrogen, the proton is 1, electron is 1. Yeah, we've established that. However, the neutron is always calculated. The number of neutrons is calculated by saying the mass number minus the proton number. The mass number is represented by letter A, capital letter A. And the proton number or atomic number is represented by capital letter Z. So this is simply equal to 3 minus 1, which is 2. Okay? So in this case, number of neutrons is 2. Number of neutrons is 2. So that's what we're referring to here. That's what we're referring to. Is that okay? So we'll be able to establish these three. So if you see the first isotope of hydrogen, you can see the neutron is 0. We've calculated that. We've shown that. Because 1 minus 1 is 0. The electron is 1 and the proton is 1. The second isotope of hydrogen, which is written like this, which is called deuterium, the neutron is 1. Why? Because 2 minus 1 is 1. Electron is 1 because electron and proton is what this number is. Electron is 1 and proton is 1. The third isotope of hydrogen, which is called tritium, the electron is 2. We've calculated that already because you say 3 minus 1, which gives you 2. Electron is 2. Neutron is 2, not electron. Neutron is 2, electron is 1, and proton is 1. Now, in this case, you can see that this one has more neutron than proton. So it gradually becomes more stable, okay, and can disintegrate to form helium. Can undergo a beta decay to form helium. Anyway, that's that for that. Let's move on to some of the decay that happens, okay, over time. For example, one of the radioactive elements is uranium, uranium-238. Uranium exists in isotopic nature. We have uranium-235 and uranium-238. We have uranium-235. We have uranium-235 and uranium-238. Okay, it exists in these two isotopic nature. Okay, it exists in these two isotopic nature. 235 and uranium-238. So they are radioactive elements. Why? Because they become unstable. Their nucleus become unstable. They can disintegrate to form a daughter nuclei and an alpha particle. Okay, can emit an alpha particle. In the tutorial, we've talked about alpha particle, beta, and gamma. So let's quickly still show that alpha particle is represented by this symbol, alpha. So in which the nucleus, the atomic number is 2 and the mass number is 4. So this is an alpha emission. When alpha particle is emitted from a parent nucleus, then this is what is being emitted. This is what we get. Okay, for beta decay or emission, We have -1 here, which we've shown in the tutorial, and 0 here. For gamma, there is no mass lost. Okay, here is 0, here is 0. Okay, for gamma. These are the 3 particles that are emitted or that undergoes that are emitted whenever a parent nuclei decay or undergo disintegration and decay. So these are what is being emitted. Now, in the case of uranium, it undergoes an alpha decay. For example, if you have uranium 238, okay, the atomic number I think is 92. So we can have 92 here. So this can disintegrate. You know the meaning of disintegration, break, decay. Okay? This can undergo an alpha decay to produce a parent nuclei. This parent nuclei, we can call it anything, for example. In this case, it will produce, this 92. In this case, it will produce thorium. Produce thorium plus an alpha decay. We're going to balance it up. An alpha decay. So, remember, whatever is on the right side must be same as what is on the left. This left, the mass number must be total mass number that is here. So, to find the number here, you must say this number minus 4 to find what is here. Because if you add both of this one on the right together, must be equivalent to what is on the left, the mass on the left. So, to find the mass here, you say 238 minus 4. Okay, we can simply say 238 minus 4. That will give us 234. That will give us 234. So here we have 234 as the mass of the element, the daughter nuclei that is formed. They can call it X, okay? They can call it X. 234. And then to find this one, we subtract the atomic number of the alpha particle. So we say 92 minus 2, which is 90. 92 minus 2, which will give us 90. Which will give us 90. So here we have 90 as the atomic number or the number of protons. Here we have 90. So this is thorium. This is thorium. So this is the parent nuclei. This is the parent nuclei. And it's a radioactive element that becomes unstable because of the difference between the number of protons and the number of what? Neutrons. Or whose nuclei gets too heavy. Parent nuclei. Okay, this is the daughter one. And this is the emitted particle, the alpha. This is the daughter nuclei. This is the daughter nuclei, and this is the alpha particle. This is the emitted radiation. This is the radiation that is emitted from the disintegration of uranium. The radiation that is emitted from the disintegration of uranium or the decay of uranium. This is the radiation. So an alpha particle has been emitted from the substance. Okay, so let's move on. So this is just quickly what I want to show you. Now this is a decay graph. And these are some of the element and their decay time, what is being emitted, the half-life. You know, every substance decays at its half-life. Okay, half of it will decay, half of it will remain. Uranium takes very lengthy years. Uranium takes about 4.5 billion years for half of the substance to decay. So it takes a lot of time, okay, for uranium. Thorium, it decays, an alpha particle is emitted. When alpha particle is emitted, thorium is formed, which is thorium 234, which is the example I showed just now. Then the thorium itself undergo a beta decay to produce protactinium. Protactinium, the mass, you know, when a substance undergo a beta decay, the mass number is same, but the atomic number increases by 1. Now let's take a look at an example of a beta decay. We just showed an example of an alpha decay. This is an alpha decay, right? Alpha decay. Now let's take a look at a beta decay. Let's take a look at an example of a beta decay. This is an alpha decay. This is an alpha decay. So let's do for beta decay. Beta decay. We will use a very simple example, the one that you will be very familiar with. Okay, for beta decay, like we said, in a beta decay, a fast moving electron is emitted. Is emitted from the parent nuclei. A fast moving electron, like as shown, is emitted from a parent nuclei. And let's take a look at an equation that shows it. You know, carbon 14. When carbon is a radioactive substance and is an isotope. We have carbon 12, carbon 13, and carbon 14, right? So when it disintegrates, it produces what? It produces the parent nucleus. To produce a parent nucleus and an alpha decay, and an alpha radiation. Sorry, I said alpha. So sorry, a beta decay. It produces. You see, we wrote the beta, but we're mentioning alpha. It will produce a beta decay whenever this happens. What happens is that when this decay happens, the mass number does not change; it remains same. So here we still go to fill it up with 14. We still go to fill here up with 14. So here will be 14, because when a beta decay happens, you can see here is 0. So it means that the number here must still be the same as the number here. However, what about here? Here, because here is minus, here will now have to be 7. You know why? Because if I write it as equation, if I write here as 6, you say 6 equal to, let's call here x. We don't know what number is here. Call it x in simple mathematics. We call it x plus, because of this big plus. But here, call it minus 1. Put a small bracket, minus 1, because there's minus 1 here. If this is an equation, what will be x? Because let's assume we don't know what is here. We're looking for it. So what will it be? What will x be? So if it's a simple mathematical equation, so you bring this one to find x, you have to bring this one to the right. It's negative here. When it's coming here, it's going to be positive. So when it's coming here, and this negative, first of all, this negative will make the whole place to be negative. Because plus minus is minus. So here I have minus 1, x minus 1. Because of this negative. So here, the whole of this place becomes negative 1. So when you move it to the left, it's going to be positive. You know, when it joins this place, it becomes 6 plus 1. It becomes 6 plus 1 equal to x. So x equal to what? 7. Obviously, x equal to 7. So x equal to what? 7. So that's how we, you know, for alpha we subtracted. But for beta decay, we are adding this negative to this place to make here 7. So you must take note. So it now produces a nitrogen atom. So when carbon 14 or that go a radioactive decay, it produces a nitrogen nuclei. Okay. So this is an example of a beta decay. In the case of gamma, the whole thing will be same. Let's say, for example, I use symbol. Okay. Let's say I call here. Let's just use symbol for gamma ray, gamma decay. Okay, let's write first gamma decay, so that we know we've given the 3 decay rate, or the 3 decay radioactive decay that is taking place in the nuclear radioactivity. Sorry, gamma. There's no y here. Okay, gamma decay. Gamma decay. In the case of gamma decay, let's just use symbol. So this is the parent nuclei. Like in this one, this is the parent, right? Even if I did write it, because I've already showed it. In the case of this is the parent nuclei, and this is the daughter nuclei. The product that is formed, and this is the radiation that is emitted. the beta radiation is the radiation. This is the daughter nuclei, this is the radiation. This is the decay substance. Okay? Or what we call the radiation, the decay substance or the radiation. Okay? Okay, so in the case of gamma, we say no energy is lost. So here, let's say the symbol here is Y plus the gamma ray. The gamma ray, there's the way we write it. The gamma ray looks like this. Okay, here is 0. Here is 0. And here is 0. So in that case, it means here will also be Z. And here will be A, because nothing is lost. Nothing is lost in the radiation. Okay? So here will still be the same. In the case, if we want to use symbol to represent this one, if you want to use symbol, here will be, let's say I use here as X, and here is A, and here is Z. So what will be our Y? The daughter nuclei. And what will be our, okay, plus, since we already have it here, let's just put the plus here. Plus this beta. Okay, plus this beta. What will be the numbers here? This one, since here is 0, the mass number is 0, so here will still be A. Y here will be what? Z plus 1. You know here is minus 1. So here will be Z plus 1. Remember when we had 6, it was 7, it became 7, 6 plus 1. So here will be Z plus 1 for the symbol. Is that okay? Now in the case of alpha decay, let's use symbol to show the alpha decay case. Let's say we have X here, and here is our Z. Okay, let's change the color. Here's our Z, and here's our A. It disintegrates. We use Y as a symbol to show the daughter nuclei, plus an alpha particle. And you must know what is emitted first, and the mass, atomic number and mass number of the particle radiation that is emitted. So when you know this, then you now know here, to get here, you must say A minus 4 to get the mass of the daughter. So you say A. Why we say A minus 4? Because it's always the mass on the right must balance the mass on the left. So here will be A minus 4. A minus 4. Meaning you subtract this 4 away from whatever is here in order to get this one. Here will be Z minus 2. Z minus 2. Why? Because whatever is on the left, on the right, must be equal to what is on the left. So if here is Z, and here is 2, you subtract this 2 away from Z in order to get the atomic number or the number of proton for Y. Okay, so this is for the three substances, radioactive substances. Okay, so these are the different decays that do happen. So this is a nucleus, a parent nucleus. When it decays, it produces a delta nucleus and an alpha particle. This helium is an example of an alpha particle. This helium is an example of an alpha particle. So it's either we use this symbol, for alpha, or we use a helium nucleus. It's either we use this symbol or we use a helium nucleus. We write 2 here, and we write 4 here. Is that okay? So either of them can be used interchangeably, okay, depending on the text. Okay, so this one happens when we say a parent nucleus becomes radioactively unstable, and it breaks, releases an alpha particle and a daughter nucleus. A daughter nucleus which is now smaller than this one, because this one is becoming too heavy. Okay, that's the main reason why this thing happens. Because the nucleus becomes too heavy, it disintegrates, becomes unstable, disintegrate. For example, this polonium, it disintegrates to produce uranium-235, and it emits an alpha particle. You can see 239 minus 4 will give you 235. it means it emits an alpha particle. And then this one also emits, this 235 emits an alpha particle to form an isotope of thorium. There's thorium-230 and thorium-231. Okay, which is, so when this one undergo a beta decay, it produces another substance. Okay, this is a graph of the atomic number against the nucleon number. That's the mass number. The atomic number against the neutron number. Okay, neutron number against the neutron number. Atomic number Z against the neutron number. That's what is plotted here. Okay. Okay. So that's a graph of that. Now this is still more example showing you an alpha decay when the radioactive substance becomes too unstable. The parent nucleus becomes too unstable. It will disintegrate, so form a new element. The new element is called the daughter nucleus. Nucleus is singular, nuclei is plural. To form a new nucleus and a particle, a radiation particle that is also emitted from the process. Okay, now these ones are just decoration. Here, they use the red to represent the number of protons and the blue to represent the number of neutrons. Okay, so in this case, you can see when an alpha particle is emitted, the parent nuclei loses to the number of protons, 2 of it is lost, and the mass number 4 of it is lost. So it means that the mass number decreases by 4, while the atomic number decreases by 2 of the daughter nuclei. The daughter compared to the parent, this one, the mass number lost 4, and the neutron number of protons lost 2. So that's the difference. That's when we say an alpha particle has been emitted. Now, what in case of beta particle? A beta particle, it means a fast-moving electron has been emitted. During beta decay, a neutron changes into what? A proton and electron. It changes a neutron. Look at this neutron. It will change to proton and electron. Okay. Electron is the beta particle that is emitted, and the proton is the new daughter nuclei. The new daughter nuclei. Is that okay? In the case of gamma, there we say there is no energy loss. There is no energy. This one, there is energy. There is no number of proton or number of electrons. It's still the same. The nucleus of the parent and that of the daughter will be the same, even if a gamma ray has been emitted. Gamma ray is just an electromagnetic wave, just like an electromagnetic wave. So it's not like alpha and it's not same. It's not a particle like alpha and beta particle. This one is an electromagnetic radiation. Is that okay? So I think these are the major things. All this one I have explained. I have given an explanation to all this one. Okay. For alpha decay, we say this one will lose 4. The atomic number will lose 4, while the proton number will lose 2. But those 4 and 2 that is lost becomes the alpha here. It becomes the alpha particle. Okay. Here example is given. You can see an example is given. You have polonium 212 and 84. Atomic number is 84. So when it undergo an alpha decay, so we have to subtract 4 from here. So I will get 208 for lead because it became a lead. And this one minus 2, it became 82. So and with an alpha particle. Okay? So I hope we're catching up. We're getting. So this is the equation I've written before. I've explained. Whenever an alpha particle is emitted, the mass will lose 4, the proton number will lose 2. So meaning you go to subtract whatever number is here. Like in this case, you can see it's 212 for the mass. 212 minus 4. You must subtract 4. Where is the 4 goes? Where does it go? It forms the alpha particle. The 4 forms the alpha. So you have to subtract 4 from here. So 212 minus 4, you get 208. Okay, and then 84 minus 2, you get 82. So you get this as a new parent daughter nucleus, and you get this as the alpha particle. Okay, so that's what it is. Now here is an example. I think this example we can look at this tutorial to understand this. It says a nucleus of americium 243 and 95 emit an alpha particle to form the nucleus of Neptunium. Identify which of the following equations below represent the decay. Which equation represent the decay? This is a very typical exam question. Okay, they mentioned an alpha particle emitted from ameritonium, and they give you the mass number of ameritonium. So we can write 2, 4, 3, and 95, right? 2, 4, 3. So ameritonium is 2, 4, 3. So we write it here. AM 2, 4, 3. 2, 4, 3. And here is 95. It says, the question says it undergoes an alpha decay. So you put a decay arrow here. An alpha, it undergoes an alpha decay. So we probably, to form Neptune, they've told you what it will form. So they give you the symbol. I think it was NP, Neptune. Okay, plus an alpha particle. So we write the alpha. You can use a helium to represent your alpha, or you just use this symbol. So this exam question, they want you to write it and balance it. So what we do, we already said to get here is like you say this number. Let's change the color to solve the equation. It's like you say 243 is equal to, turn it to a mathematical equation, is equal to, you don't know what is here, you can call it x. You say it's equal to x plus 4. You can turn it to a mathematical equation. It's equal to x plus 4. So find x, meaning find what is here. What is the mass? This top, we are considering only for the top first, right? We are considering for the top. Right? This is what we are solving. So to find x, you have to move 4 to the left. So x is what? X is 243 minus 4. 243 minus 4. That would be 239, right? 239. Okay, so we've solved for this. Now let's solve for the bottom one, the proton number for the proton. So we also do it like equation. So you say 95 is equal to, you can call this one, if you like another symbol, you can call it y or x2. You can use x1 here and use x2 here, it's up to you. The point is for you to be able to solve it. Plus 2. So 90, whatever is here, which is 95, is equal to what is here, which we don't know, plus 2. So to find x2, we have to move this one to this side, and it becomes minus. So x2 is simply 95 minus 2. 95 minus 2, which is 93. So now that we found the mass number and the atomic number for this, so we simply put them here. We simply come and put them here. So which means here is 239. This one here is 239. In exam, this type of question you get 3 marks or 4 marks. So here is 239. Then you must show your working if it's a theoretical question. And here is 93. You must show how you get the numbers. If you just write this number and this number here without showing this work, these two solvings, they will give you only 1 mark out of 3. So it's usually 3 marks, but you must show your solving. Okay, normally doing this one, they give you 1 mark. Doing this one, they give you 1 mark. Putting both of them together here, you get another 1 mark. So you get 3 marks. Okay, this is how the exam flows. This is how it goes. Okay, so that's the question. That's what they ask us. But let's take a look at the tutorial and see maybe if they have more questions than we've asked for. Okay, let's listen to the tutorial.
to look at, and as usual we'll start through by reading through the question carefully to make sure we understand what we have to do. A nucleus of americium, and there's a symbol for americium there, emits an alpha particle to form a nucleus of neptunium. Identify which of the equations below represent this decay. So we've got 4 different equations here, all showing alpha particles being emitted. And here is our americium decaying into neptunium, which are 2 quite exotic radioactive materials, but nevertheless it's just an example we need to work through. So just check the question again. We need to identify, so just tick one of these boxes, whichever one we believe is the correct equation, and very importantly that we're emitting an alpha particle. So first and foremost, we need to remind ourselves what an alpha particle is. And here I've got a screen grab of some of the theory, and that over there is the representation using our standard notation of what an alpha particle is. It's just a helium nucleus, which means it has 2 protons and 2 neutrons. 2 plus 2 is 4. So my nucleon number is 4 and my proton number is 2. So immediately I can remove option 2 and option 3 because they have been put in there to confuse you. This is not an alpha particle. These are the numbers that would be associated with a beta particle. It's not part of this question, which means it's either that one there in the first one or this one over there. Now, to make sure that my equations balance, whatever that number is, I know that that's 4. This number over here must be 4 less than that. So here's an example. Here's polonium, and it's decaying into something. It doesn't matter what it is, but you'll see that that 208 plus 4 gives me 212. That's important because it means that my mass is being conserved. Similarly with the proton number, 82 plus 2 gives me 84. So if I go to this one here, I've got 243 nucleons on this side going to 247 plus 4, that's 251. So it's not this one because my nucleon numbers are not balancing. Similarly, my proton numbers are not balancing. I've got 99 protons on this side, 95 protons on that side. I've eliminated that one, I've eliminated that one. 239 nucleons plus 4 gives me 243. 93 protons plus 2 gives me 95. So in this case, the last option is the correct answer.
Okay, so that's it. That's the explanation. I've done the calculation and I've showed you. Okay, here they're explaining the beta decay. I've already explained the beta decay. I say in the case of beta decay, this one, because this one is -1 here, you're going to add it to the z. Because when this -1 is moved to this side, it's going to be +1. So in order for them to balance, you must put plus here. Because z plus 1 minus 1 will be equivalent to z. So if you compare the law of conservation of mass, what is on the left will be equal to what is on the right when there's +1 here. So because the +1 will be eliminated by the -1 in order for z to remain. So this is the symbol equation for beta decay. This is symbol equation for beta decay. We've already looked at this decay concept. Okay. So here is another tutorial for a beta decay question. Okay, we can go through it ourselves quickly, or we go through the tutorial, whichever one is okay. A radioactive decay can be represented by the following incomplete equation. 2,3 incomplete equation. 233 decays to 233. 91 decay to 92. Okay, we already know the type of decay. Okay, this is going to be beta. You know why? Because this one has decreased. So, you know, beta has -1. In order to reduce this one to 91 back to the original 91. You know, this 92, yeah, so there will be a beta and the 0 is on top. So, which means the mass here will be same as the mass here because the 0 is on top of beta decay. So, this will be a beta decay. So we can go through the tutorial just to hear it, but this is a beta decay. So these are the type of exam questions you see.
Here's a question for us to look at, and we're going to start by reading through the question and having a look at what is expected of us. A radioactive decay can be represented by the following incomplete equation. And here we have two large nuclei, and we have a decay from this nucleus into this nucleus over here. Use the keywords provided to complete the equation. And we've been given alpha particle, beta particle, neutron, proton, emitted and absorbed. So we need to make a statement out of these words that completes this nuclear reaction or this nuclear equation. So simply we have to complete the equation and we have to use the keywords. So it's a radioactive decay, and what's important here is that it's incomplete. There is something missing from this decay. Now, the two types of radioactive decay that we can deal with simply are alpha decay and beta decay. And as a reminder from your theory, that's what these two types of decays look like. So in alpha decay, I see that the nucleon number, that's this number at the top here, the nucleon number decreases by 4 and the proton number decreases by 2. And in beta decay, the nucleon number stays the same and the proton number actually goes up by 1. So if we have a look at what we've been given here, we see that our nucleon number is staying the same and our proton number is going up by 1. So that's pointing us in the direction that this is actually a beta decay. So there we go. The proton number increases by 1 while the nucleon number stays the same. So this is an example of beta decay. So the first thing is, it's a beta particle. So we can ignore the fact that it's an alpha particle and definitely ignore the fact that it's a neutron or a proton. Those are not emitted in a beta decay reaction. Now, is it emitted or absorbed? I kind of just gave it away, but just to remind you, this is beta decay here. If the particle is on this side of the reaction, it's emitted. And if it's on this side of the reaction, it's absorbed. In beta decay, the particle's on that side. So what we can say is to use the two keywords that a beta particle is emitted in this type of radioactive decay.
Okay, so we've got it that, right? So the last part is the gamma decay, which we've shown. We said for the gamma decay, the mass stays the same for both the parent and the daughter nucleus. Then for the atomic number or the number of protons also stay the same. A gamma ray is emitted. A gamma ray is emitted from this. Okay, so these are now questions that we can deal with, examples, which you can find in the exam. It's a nucleus of 84 protons and 126 neutrons. Okay, remember this neutron, this is not the mass number. 126 neutron, or they go alpha decay. Okay, it forms leads. It forms lead, lead, which has an element symbol Pb. Okay, so we can simply, first of all, we can add this and this together. The number of proton, number of neutron will form the mass number. So we can simply do that. 126 plus 84. We can do that quickly and see what is the mass number. 126 plus 84. So what do we get? 210, right? This plus this, you get 10. You carry 1, bring the 1 here, 12 plus 10. Carry 1, bring the 1 here, 10. 10 plus 1, 11, right? Bring the 1 here, 210. Yeah. So we get 210 for the mass. Okay. It undergoes an alpha decay. Let me say, for example, this is the element. The mass number is 210. The mass number is 210. and the number of proton was 84. And they say it undergoes an alpha decay. So if you undergo an alpha decay, it means you get a product, and they measure the product. Okay, they say lead, right? So let's write lead for this. So it forms lead, Pb, plus an alpha decay, plus an alpha decay. So the alpha, you can use this symbol or you use the nucleus. So plus alpha decay. So here we can begin to find what is here. You know, this is always minus 2. 84 minus 2 you get here, it will be 82. So let's change the color. So we get here to be 82. Right? And then to find what is here, we're going to say 210 minus 4. 210 minus 4 will be 206. So here will be 206. Because to always find what is here, you must say, because here plus here, law of conservation of matter, mass, is that the sum of the mass on the left must be equal to the sum of the mass on the right. So this plus this must be equivalent to 210. So this is it. So they probably going to ask you for the mass number and whatever of lead. This is it. You've done it, and you get your case. Okay, you get your case right. Okay, so that's what it is. Okay, so here if you look at which one is the option in A is this in the exam. A is this, B is this, C is this, D is this. So if you look at the option, it's a nucleus with 84 proton and 126 neutron. So where many students will make mistake, they will think this is the mass number. They will put this 126 on top. They will put no, this is just the neutrons, number of neutrons. So 84 protons and 126 neutron undergo alpha decay. So it forms lead. When it undergoes an alpha decay, it forms lead. Right? Which has the element symbol Pb. That's for lead, Pb. So which of the isotopes of lead picture is the correct one formed during the decay? Which one is the correct one formed during the decay? Obviously, it's not this one. It's not this one. This one is the original element that decayed. The original element that decayed. Right? This is the original element that decayed. It was 210 and 84. But so this is not the parent, the daughter nucleus. This is the parent nucleus. And this is not what they ask you. And it's not this one. So the answer is simply, so this and these are completely wrong. They are out of it. The answer is simply this first one. 206 and 82, as we have shown or demonstrated in the calculation. First, we found the total mass number, and we wrote it for the element. And then when it undergo an alpha decay, means we have to subtract 4 from the original one to get 206 here, and we have to subtract 2 from the original proton number to get 82 here. So we get this atom. Is that okay? So let's move on. So you see, they say the answer is A. Just like we have calculated. The answer is A. Just like we have calculated. So they've done the calculation anyway. So they arrive at what we arrived at. Okay, here's another one, which the student, any good student, can quickly try on his or her own. You can pause the video and then try this. It's a nucleus with 11 protons and 13 neutrons. So 11 plus 13 is 24, right? So the mass number will be 24. That grows a beta decay to form a magnesium. So the nucleus we don't know, we can use X for the nucleus. Anytime they give you something, they didn't tell you the name, you can just simply use X. So a nucleus with 11 and 13, 11 proton, right? 11 proton, so I write 11 here, and 13. So if you add 11 plus 13, you get 24. Because 11 plus 13, you get 24, right? Why are we adding 11 and 13? Because it has 11 proton and it has 13 neutrons. And mass number equal to number of protons plus number of neutrons. The mass number is equal to the number of protons plus the number of neutrons, which gives us this 24. Then the question says it undergo a radioactive decay to emit what? A beta particle. So here they measure magnesium. They say the daughter nucleus is magnesium that is produced, that is emitted. Always emitted, like we said, when you have the radiation on the left side, you say it's emitted. If you have the equation where the radiation is on the this left side, you say it's absorbed. When the radiation is on this right side, you say it's emitted. Okay? Okay, our tutorial already explained that. So you say plus a beta particle. You must know the symbol for a beta particle. And here is -1. You must know here is -1, and don't mix it. The top is 0. So instead of write the -1 on top and put 0 at the bottom, you're going to miss it. So if that is the case, you know the sum of what is here must be equal to the sum of what is here. So here is 0. Here will also be 24. Let me use a different color to show that we are now putting the answers. Okay, so here will also be 24. Here will be 24. Why? Because 24 plus 0 equal to 24. The 24, you know the sum of the mass on the left must be equal to the sum of the mass on the right. So this is the right one. The sum of the mass on the right, same as the one on the left, and the sum of the one on the left, also same as the one on the right. So 24 equal to 24 plus 0, which is 24. So this one is balanced for the mass on top. Now for this one, like we said, when you have a beta decay, you're going to say whatever is here plus 1. Why? Because this minus, when it comes here, it becomes plus. So here will be 12. And you know magnesium atomic number is 12. And the mass number is 24. This is an isotope of magnesium. So this is the equation you write for them in the exam. And then you get your marks. So these radioactive equations are easy if you follow what we're doing and follow our videos and pay attention. And repeat them when necessary. The calculation. So you see the answer is D. 12 and 24. The answer is D. Is that okay? So these are the example, and so today we've come to the end of our class. We've come to the end of our class today, and I hope we catch you up again in our next class.